It's good to be back in an old LS. This is a 6-liter. I think it's an L96. It might be an LC8. But it's got a 6L80 transmission. Pretty simple Jeep. Drives really nice. 6-liter's got plenty of power. What's he got here? 35s. You got 35-inch tires. You don't need much more than this. The 5.3 LT is very similar in power. So this looks like a new crate engine. We've actually had a line on them for a little while now. It's got the Motec battery tray. Look how much room you got there. Everything else is pretty typical. Gen 4 computer, Motec PDC. This engine has quite a history. It really has its roots in the early Gen 3 LQ motors, the LQ9, LQ4. Then it went to the LY6 in around 2007 when the Gen 4s came out. Then that evolved into the L96, which has variable valve timing and flex fuel capability. If you look at these injectors compared to an early LY6, they're taller. They can flow more for the flex fuel. Guys get a lot of power out of these. I think they got the good heads on them already, and you know, with a good intake and exhaust and all that, they're pushing 400 plus horsepower. So it's as mild as can be. These engines will sit there and idle at 500 RPM. Air conditioning, the heat, the cold, you guys know the routine on the 6-liters are pretty much bulletproof. Probably the most solid engine out there for any engine conversion. They can go the distance regardless of the environment. This morning we're in an early model JK with a 6-liter L96, I think. It could be an LC8, which is essentially the same engine. And as you can see, the 6-liter has no problem. We got some tall gears in this. We're running about 1800 RPM going up the parkway, and it's in top gear and it has no tendency to shift down, so got a lot of torque. In my last video we talked about setting monitors, but I think this is a more comprehensive subject. Now for a lot of you this is just going to be boring, it's techno nerd stuff, and I do know that a lot of customers call me and they want to talk about this stuff, and they want to talk about it not just as it applies to their Jeep, but they're genuinely interested in the technology and where we've come from and where we're going. And I think this makes a lot of sense right now because we're in this transitional period where we're trying to have EVs or electric vehicles forced upon us. Most of the experts agree we're just not ready. The EVs do have their place. If you're a commuter in a city and you don't drive very far and you have access to good charging stations, that's great. But if you're like most of us Jeepers and you're gonna get in your Jeep and drive hundreds and sometimes thousands of miles on a trip, one, the EV vehicles don't have the range in these heavy loaded down vehicles, and two, you're always going to have that anxiety about getting to a charging station, and if you do get to a charging station, is it going to be broken? Is it going to blow up? Is there going to be a crowd? So I just don't think the EVs make sense yet in heavy trucking and heavy SUVs, etc. And the gas motors are so efficient right now. That's what we're going to talk about, is how we kind of got here. And when you consider that you can get 40 miles to the gallon, which I just did in a trip to Salt Lake in a small car, on 1 gallon of gasoline, then you got to figure how much would that have cost in an EV vehicle when I factored in stopping at the charging station, the distribution and production of that electricity to power my car, the initial cost of the car, which is higher. And I'm not going to go into it, but you guys get it. So I want to go back about 50 years. If we look at the 1970s, it was pretty much a free-for-all. Emissions equipment really started in California in the late 1960s. And I was born in the 1960s, and I do remember that brown haze, or that smog, which is fog and smoke combined. So by the late 60s, early 70s, the ARB in California, the Air Resource Board, was blazing a trail for emissions equipment. One of the first emissions devices was the PCV, or the crankcase ventilation system, and that was a big success. It removed a lot of contaminants from being moved into the atmosphere. We had air systems to complete combustion. By the early to mid 70s, we had the EGR, or exhaust gas recirculation valve, which reduced NOx. We also had the catalytic converters come in, which basically took most of what was left over, the bad gases or harmful gases, from primary combustion and converted them into better gases like H2O, CO2, etc. But things really started to change in the late 80s. In the late 80s, it was apparent we had to clean up these engines. Most of the engines running around, whether it was the Ford, Chevys, Chryslers, and I'm not going to talk too much about the import. The Asians and Europeans had some pretty sophisticated small displacement engines because that's what they primarily built for their country. They were starting to take over our good old American V8s. Our good old American V8s were getting choked down with emissions equipment. Most of them were designed back in the 1950s, and we're pushing out 200 horsepower in a 400 cubic inch V8. Now, there was a second kind of revolution in the redesign of these engines when we finally ditched, and that started to happen in the 1990s, where we finally ditched the old architecture, where engines were designed in the 50s for 1950s emissions, and then went to ground-up designs that were designed with emissions in mind. So in the late 1970s, some new stuff started coming around, and that's kind of when I got into engine conversions. We got the 4-speed transmission. Remember the original Turbo 700 R4? That came out in like the early 1980s. I think I got a 1981 Camaro Z28, and it had a lock-up torque converter and a Turbo 350. So there was another step forward. The lock-up torque converters are everywhere now. Back then it was on and off, and it wasn't really well controlled. Today they're pulse width modulated and very sophisticated. Your transmission might just loosen the converter up rather than shift. So we were starting to see the genesis of this new technology. Most of the vehicles back then ran on carburetors. There were fuel injection vehicles around, of course. They've been around for a long, long time. But the carburetor wasn't exactly the most efficient device to deliver fuel, especially on like cold starts and deceleration and other modes other than at a steady cruise. We had power valves, and we had stepped metering rods, and we had metering jets, and the carburetors were very, very sophisticated. And they even went one step further. In the late 70s, early 80s, they went to the feedback carburetors. And what that means is they use an oxygen sensor to sense the oxygen in the exhaust. And my last video kind of talked about the oxygen sensor. And then they would vary the output of the carburetor based on that feedback. So it's a closed loop feedback system is what it's called. So rather than just putting an output out, it looks at what's going on, and then it has input sensors, air intake temp, RPM, and obviously one of the most important is the O2. It looks at that, and then it comes up with a fuel strategy. And the early systems used these block learn tables that were pretty simple. The engine was either lean or rich, and they used the oxygen sensor to control stoichiometric. And then they had open loop modes. Closed loop modes meaning you're running off the O2s. Closed loop modes would be like cold start, performance enrichment, all that. And we've talked about that, so I'm not going to go into it. But things still had to get better. The closed loop feedback carburetor systems were not very good. And by the mid to late 1980s, we went into simple fuel injection systems. GM was really big into throttle body systems, and they were great. One of the advantages of the throttle body system is they could basically take an existing engine, take the carburetor off, and bolt the throttle body on, and you got a fuel injected engine. And I ran throttle body engines for years, and when lean cruise was available and legal, I used it. I actually was getting really good mileage in the late 80s, early 90s using these lean cruise throttle bodies. But the throttle bodies suffered from some of the downsides of the carburetor, and that is wall wetting. When you take fuel and you got to put it through an intake that is all convoluted, the intake runner could be like an amorous snake, and you've got to push that through, especially when you have varying intake manifold vacuum. Because remember, if you got a big cam, you don't have intake manifold vacuum, you got pressure. And when the fuel air mixture is under a vacuum, it tends to stay atomized. But then when that pressure changes, it could turn into droplets of fuel and just wet on the side. So they weren't very efficient. And in the morning, before the thing warmed up, again, the fuel delivery was not optimal with the throttle body. But I will say it was a ton better than a carburetor. Some of the big advantages the fuel injection had over the carburetor, including the throttle body, was drivability. You guys that drove carburetors off-road know what I'm talking about, especially if you have like a center pivot Holly, which is made for going around turns, not acceleration. They also had the side pivot that was meant more for acceleration. But going up and down these hills, the carburetor would flood out. You'd have to like floor it, keep the engine running. Carter and others came out with spring-loaded needle and seats. It was just a constant battle, lower your float level to keep these carburetors performing off-road. Nice thing about throttle body fuel injection is you turn that key and it's going to run. It's going to run in the morning, it's going to run going up a hill, it's going to run going down a hill. And that's kind of one of the reasons the Germans used it in World War II, because the carburetors of the day, while very sophisticated, and some of them almost were, I forgot what they called it. I think they called it carbureted fuel injection, but they were kind of like a carburetor with an injector inside of it. They evolved, it was just a natural progression going from a carburetor to fuel injection. But the closer you got to fuel injection, the better performance you had, especially like in steep dives. Some of the fighters would go inverted to go into a steep dive because if the carburetor went under positive G's for so long, it would flood out and all this. So fuel injection made a massive improvement in drivability. But the government wanted more. The engines were still dinosaurs. We were still tacking on all these corny systems. I don't know if you guys remember the old Chrysler lean burn systems, and Honda had their stratified combustion chamber, and GM took their small block and updated it with the newer heads, put a serpentine belt drive on it, put port injection on it, and everything was an incremental improvement. Everything made it better and better. So manufacturers were driven to get better performance, economy, and mileage, and it was obvious that major changes had to be made. 1981, something called Onboard Diagnostics 1 came out, and it helped mechanics identify the failure or emissions-related failures because it required the vehicle to store emissions-related trouble codes. Now, the vehicle was not diagnosing itself. It did not have monitors. It was not nearly as sophisticated as OBD2. So in 1981, they said, you got to throw basic trouble codes. You know, like if your map sensor goes bad or a coolant temp sensor fails. And it was actually a pretty good setup. I remember in the GMs and the Fords, they were pretty accurate. A guy came in and said, hey, you know, I'm not getting a very good mileage, something's going on. You plugged in and you had an intermittent code for a coolant temp sensor. You check the coolant temp sensor and the circuit, you fix it. And that's how simple it was back in that day. But the problem is Ford, Chevy, Chrysler even went to a primitive CAN system, meaning a controller area network where multiple modules are slaved together, and we'll get into that later, probably in the next video. But they did that early on with Mitsubishi. It kind of is the genesis of what's going on right now in the CAN networks, and I think it was 2004 that the government required CAN networks to come around. As poor mechanics, including me, I had to have a scanner for a Ford, a scanner for the GM, a scanner for Chrysler. They all pretty, you know, the DRB and the Tech 2, and Ford had their EEC systems, and Chrysler had their SMEC systems, single module engine controllers, and it was a nightmare. And that doesn't even include the imports. Get a Honda, an earlier Honda, when they went to computer control. You had the engine performance, you had an ABS module, you had chassis stuff going on. The BMWs were famous for that. I had a whole toolbox, a rather large Matco toolbox with a hutch completely filled with electronic equipment to try to diagnose everything. So the government said this is kind of ridiculous, and they felt that by standardizing the language in the connector would not only reduce the tool count that the mechanics had to have, but it would increase the probability of fixing a vehicle. Because now anybody with a single scanner could plug in and get generic codes. So anything that came into your shop, you had one scanner, you plug it in, you get these generic codes. Now that doesn't mean the other scanners weren't still required. If you're working on a Mercedes or a BMW or a Ferrari or even a GM, if you specialized in that brand, you needed dedicated tools. I had 2 or 3 Tech 2s back in the day. I remember when Delco, what do they call it? The Technical Delivery System, TDS, they called it something else. SPS, service programming. Anyway, they would send you a disk that you would put into your PC, and that would download all the engineering files. We didn't even have anything online. And what ended up happening is, in order to run a shop and support just the domestic brands, mechanics had a huge investment in tools and equipment. So then it became more profitable to just specialize in a brand. That's why you see like Mercedes only and a GM garage or a Ford garage, but most garages tried to handle all the domestics and then took the imports on the side. That all changed in 1996. Like I said, OBD1, Onboard Diagnostic 1, in the early days was required to store basic trouble codes, did not diagnose the vehicle. I remember in 1981 working on the GM vehicles, they had CCC, Computer Command Control. And what they did is they added a solenoid into the carburetor to control mixture, and they added a single wire O2 sensor, which is extremely primitive, but back in the day, you had feedback. You didn't have feedback on a cold start, you didn't have feedback at low speed or at a stop. You basically went into an open loop mode, but you had feedback for cruising. The problem with these systems was they were all mechanical. Imagine this solenoid running thousands and thousands and millions a cycle. The feedback carburetors were really not the ultimate in reliability. So a lot of guys just tore them off and put on a Rochester or whatever. They ran pretty much just as good. The old carburetors really were sophisticated. You know, they had acceleration circuits like accelerator pumps. They had power valves, which is essentially the same as our performance enrichment today. They had idle transfer ports, so when you went off idle to a cruise, it was smooth. You didn't have a gap. They had dash pots that would slow the closing of the throttle, because just slamming a throttle shut's not good. That could cause hydrocarbons and misfires. But by the time you added on the air systems and the exhaust gas systems and the catalytic converters and all this other stuff, air management valves, these things just got kind of out of control. So it was apparent that a new generation of engine designed from the ground up for emissions were required. In my opinion, the first LSs were really a huge step because they went to a whole new architecture. They went to a 6-bolt cross-bolted, all aluminum block. Most of the LSs got rid of the exhaust gas recirculation valves. They got rid of the air systems. They got rid of a lot of the complexity that was tacked on to the old-fashioned engines to try to make them meet the standard. So now we had a pure engine that we could focus on performance and economy. I gotta say, when the first LSs came out in the late 90s, you could take a 5.3 LS and it was pushing over 315, 320 horsepower. And we would take out a 5.7K motor, which is a small block Chevy with port injection or throttle body injection, that was rated at 180 horsepower. We put that 5.3 in and it was almost double the horsepower, and it was a smaller engine. All the ones that we did, we used to do them in the old body style trucks and the new body style trucks. Every customer was just amazed how much more power, how much more economy. They would come to me and say, hey, I can tow my boat now from Vegas to Lake Mead and I'm not struggling and my economy has gone way up. So it really was a revolutionary change going from the small block from the 1950s to the LS in the 1990s. The other manufacturers kind of followed suit. The one manufacturer that was not very innovative with their V8 was Chrysler with the Hemi. They did reintroduce the Hemi, but they kind of kept the old architecture, the iron block, the dual valves, which is fine overhead. The new modern iteration of the Hemi is not really a full Hemi, it's more of a semi-Hemi, which the big block Chevy kind of was too. But the Hemi is still a fantastic engine. I've got nothing against the Hemi. I just like the LT and the LS better. They're lighter and smaller and they can put out the power. Fast forward to 1996. OBD2 comes out. OBD2 is now requiring that not only does the operating system have to store trouble codes that can help a mechanic or an inspector diagnose what the problem is, but it has to diagnose itself. So the way it does this is by monitor. Remember the hall monitors at your school? Well, that's kind of what these monitors are. And they break them down into subsystems. You have one for misfires, you have one for O2s, you have O2 heaters if that's available, you even got air conditioning, comprehensive. There's not a lot, but there's enough monitors to verify that that engine is running properly as you drive down the road. That way when you go to an inspection, all they have to do is plug it and talk to your computer, and your computer says all the monitors are set, nothing is out of range, everything is good, there's no emissions related trouble codes, and you pass. Now that's in a perfect world, and with modern operating systems, I think that's pretty much true. But after 1996, there were some bumps in the road. Mechanics couldn't find data link connectors. I think it was Acura, put the data link connector behind the ashtray in the center console. So you had to take the center console apart to get to the data link connector. So of course the feds came out within the rule. It has to be within so many inches off the center of the dashboard and apparent or readily visible to a mechanic. Running these monitors is kind of a complicated thing. The manufacturers buried this diagnostic data in the operating system, and even if you have EFI Live, HP tuners and all that, you can't access it. You can change the operating system, but this emissions monitoring is kind of in the background. It was very difficult with some vehicles, Hyundais, Mitsubishis, BMWs. Some of them, the monitors were almost impossible to set. Like I said in the last video, you had to stand on your head and floor the vehicle and come to a stop without touching the brake and all this weird stuff. Dealers were getting involved trying to set the monitors, and it just turned into a nightmare. So the EPA did allow exceptions for monitors, but there had to be something better. So as time went on, the monitors evolved so that in a properly running vehicle, these monitors would set in a reasonable amount of time. And for the most part, that's true. However, with these ultra-low emissions vehicles, it's getting harder and harder to set these monitors because the tolerances are tighter and tighter. And the slightest thing can inhibit a monitor. If you have a slight evap leak, the gas cap has a very slight crack. You have a major leak in the evap system, which is like a 455, and I think the early JKs even had a thing in the dash that would say, check gas cap. You have something called small leak, and a small leak cannot just be tested at random. It has to be tested under the right conditions, temperatures, and the system can pick up an extremely small leak. And the way manufacturers test that is different. Jeep used the diurnal vacuum overnight to build a vacuum in the in the evap system or the fuel system, and they use a switch to monitor it, which is pretty primitive. But today pretty much everybody uses a fuel tank pressure sensor, and they can monitor that fuel tank pressure sensor whether the engine's running, the engine's off, and the key is out of the vehicle. And sometimes in order to enable this monitor, and monitors have to be enabled for an ignition cycle, which means if some other monitor dependent test is either not set or has failed, that monitor will not enable. So you can drive it all you want and that monitor will not set. So in order to enable a monitor, sometimes there's condition, like you have to go 2 drive cycles. And a drive cycle isn't just starting the vehicle and driving to the store and back. A drive cycle could sometimes mean 10 miles, so many minutes, and then temperature comes into it. A lot of the monitors won't enable unless you're below, I think it's 91 degrees, but I find it's more like 85 degrees. And this isn't just a GM thing, this is an everything thing. I've seen the imports, I've seen Hemis, I've seen everything have problems setting monitors. We had one at one of my shops, it was a Lexus, and the CAM, or the Keep Alive memory system, when you key down your vehicle, the computer stays alive. There's a constant power to the computer to hold the adaptives in the transmission and the adaptives in the computer, things like your spark adaptives and fuel adaptives, but it's also for emission. It keeps your emissions monitors up to date. Well, with the Lexuses, they actually had a problem in the computer where the CAM, or the Keep Alive, would power down after so much time, and that would clear the monitors. Now, things got a little bit more complex in about 2004. It became apparent that by networking modules, we could make a simpler and cleaner vehicle. So rather than having wires go everywhere, we had signals going everywhere. The CAN system was born. Control area network was used in heavy equipment, it's used in boats, it's used pretty much everywhere. If you look at the old Chryslers, they had 2 coolant temp sensors. They had one for the gauge, and they had one for the computer. Now the computer used it for fuel metering and other things, like if it's overheating, it won't allow the air conditioning to engage, so it filtered the air conditioning. And then of course the gauge was using its sensor to control the gauge. So with the CAN system, the theory was, why have 2 sensors, 2 sets of wires, all that waste? Why not just have one coolant temp signal and then send it over a CAN network, which is packets of information, first to the computer and then to the instrument cluster, because CAN systems do have priorities. Certain high-speed CAN, like ABS or engine performance, have priority over low-speed signals like radios and things. The power required to drive all these systems went down, efficiencies went up. The problem with the CAN system is it is a complex network of modules based on packets and information delivery. That can always go wrong. Now, CAN systems now are robust and they have self-healing properties, and they can ignore modules that are out of range, and they've gotten better and better. Like I said, back in the 90s, I remember the early CAN systems from Mitsubishi and Chrysler, and man, they could throw you for a loop. I had one, I think it was the L-body, it was the Concorde Mitsubishi thing. The coolant temp gauge kept freaking out on the dash for this customer. So of course we checked the coolant temp sensor, and other shops replaced the temp sensor and replaced the computer. Nobody was fixing the problem, not even the dealer. Well, it turned out this thing had a bad ABS module, and the ABS module was corrupting the CAN signal in that early system, and it wasn't capable of diagnosing itself. So imagine informing the customer that you have to replace the ABS module to correct the coolant temp problem. But things have evolved and things are much better now. Having a CAN network can deliver a lot of information more efficiently, but it can also deliver problems. So if you have, like, let's just take a Rubicon for example, the sway bar module, and modern vehicles can have dozens of modules. You know, you got wireless modules, you have the TIPM, which is the gateway module. I call it the grenade with a pin out. You got the ECM, you got the TCM, you got the PCM, you've got the cab module, which is your cluster. You get all sorts of modules in your JK, and the JLs have them in a lot more. But let's say your sway bar module freaks out. Let's say you got mud into the connector, and it shorts out the CAN network. You guys have seen what happens. The windshield wipers can go off, the horn can honk, the lights can blink, and the engine could even die, all because of a sway bar module. And while it's getting better and better, I think a lot of you guys know in your JK some of the CAN problems that you've had watching things freak out. And again, I do understand that this may be a little boring for you guys, so if you're not into this techno stuff, all you want to think about is your Jeep, you might want to just skip these videos.